let's move on to today's topic. And instead of just going through this material, me teaching you guys, I want you guys to think critically about a few of these questions I've got on the screen. And then we're going to answer them over the next 10 or 15 minutes when we go through the teaching portion. So I've got 3 equilibrium expressions for sparingly soluble solids up on the screen right now. With regards to the first one that contains silver carbonate, the same compound we saw in our warm-up, is it more or less soluble when I add acid to it? So imagine I have a saturated solution of silver carbonate. Will it become more or less soluble? Will more of that solid dissolve? Will more of it actually precipitate out? Now, what do we think? Ellie, you had your hand up.
More soluble because the acid uses up the CO3 and then flavor the full reaction.
Ooh, you think the acid reacts with one of those products, and you said which product is it?
The
Carbonate ion.
And then it favors before the reaction because it's released.
Less of it to replace it. You're thinking of what we call Le Chatelier's principle last year at level 2, right? You know, what would drive the reaction forward, maybe? Nellie?
Well, I was going to say that there might be an acid-base reaction, but no, because that's a salt.
In solid form it is, right? But
Yeah.
there's a small amount of that solid that is able to dissolve, and so the solution does contain some of those ions in very small amounts, right? And so what
I
you're
thought
suggesting,
maybe it would precipitate more into Ag2CO3,
so maybe it goes the other way.
but that doesn't make a lot of sense.
Maybe we'll have a look in just a minute. But let's look at the second equation, see what we think happens there. So we have silver chloride this time, a sparingly soluble solid, but some of it does dissolve to form silver ions and chloride ions. Will it be more or less soluble when ammonia is added? Ammonia, of all things. What are some properties that we know of in regards to ammonia? Yeah.
I don't know if I mean, it's a base.
It is a base. I heard you say that too.
It forms ligands. Is that useful?
Ooh,
Doing something?
you nailed 2 things. It's a base. It forms something called ligands, which is a new concept for many of us, which I'm sure we'll talk to later today. Okay, and the third equation. What do we think is going to happen with the solid? Will more or less dissolve when zinc hydroxide is what we've got, and if the pH is really acidic, less than 4, will more or less of it be able to dissolve? What about when it's kind of in the middle, like not too acidic, not too alkaline, between 4 and 10? And what about when the pH is really alkaline, above 10? These are all 3 different situations, and they may have different answers. So does anyone want to speak to one of those scenarios? Maybe you can't predict all 3, but can you tell me what you think will happen in one of those scenarios? So it's zinc hydroxide, right? And we're either in really acidic or really alkaline conditions or somewhere in between. Yeah. Jimmy?
So if you're in acidic conditions, you would have free protein H plus ions.
Yes.
Bond with OH minus produce water.
And
Thus, more zinc hydroxide would dissolve because OH ions are being used up.
so
by something else.
similarly to what I think Ella said for the first one, shifting equilibrium to the right towards the products to replace those hydroxides that might have been consumed in that neutralization reaction. Yeah. So that's a really good answer for what happens when the pH is acidic, less than 4. When it's in between, do we have any guesses?
Pretty insoluble. The
Pretty insoluble.
transition metal hydroxide.
Yeah.
So that's soluble.
So you're thinking without a lot of hydrogen ions to neutralize the hydroxides, it's not going to really help it become more soluble.
Yeah.
It's probably going to become pretty insoluble there. And what about at really alkaline pHs? So we have a really large concentration of hydroxide. What's going to happen?
I don't know why, but it does become soluble. What happens actually, but it's soluble in base.
So we think it's actually, it seems kind of contradictory.
It does both.
No, product.
You can't explain it in terms of really what we know about Le Chatelier's principle right now yet for many of us. When you have an excess of hydroxide at a high pH, wouldn't that shift it towards the left to form more reactant? You would think?
Yeah, you think so.
You would think so. but Oscar's saying that there's something unusual happening with really large concentrations of hydroxide that might drive it the other way.
Yeah, I think it forms zincate. So it's actually maybe a chemical reaction in that sense.
It forms actually a complex ion,
Yeah.
really, yeah. So we're going to be looking at something called complex ions today. But the first one doesn't require knowledge of a complex ion. The first one is just, like you said, it's an acid-base reaction where the carbonate's going to be removed by the acid at a low pH, and that will just drive it towards the right. That's typical Le Chatelier's principle stuff that we know from last year. So let's go into that scenario. So the effect of acid on solubility. So this slide's all about acid. We will look at base later on. So if the salt contains a carbonate, you know, this is the first of the three equations we just predicted. It will dissociate into its ions, of course, and the acid can neutralize carbonates. And this would reduce the concentration of carbonates, and accordingly, the principles of equilibrium say that if a product is removed, and in this case carbonate is used up, the reaction will increase in the forward direction, favoring the formation of more products to replace the depleted carbonate. So acids increase solubility if the salt contains a carbonate. That is the main message there. Okay, so question?
It's not relevant right now.
Okay. So I think this is a good way to ease into this topic of how solubility can be adjusted with pH, because this is something we could have predicted last year. We're mostly familiar with the idea that carbonates react with acids. If you've researched any sort of like ocean acidification thing, you'd be familiar with that.
Yes.
Yeah. Cool. So that's one way we can dissolve more if we wanted to make it more soluble. So we've answered the first scenario. So I've just bolded the correct answer. It will become more soluble, okay? Now let's look at the second scenario where we have silver chloride. Is it more or less soluble when something called ammonia is added, okay? So NH3, ammonia, we talked about how it's a base. We talked about how it might form something called ligands around the transition metal ion. Let's have a look at it. Now, in this case, ammonia is a base. So we're looking at the effects of this type of base on solubility. And in this scenario, ammonia or hydroxide, in a lot of cases, will form something called a complex ion around select transition metals. And I'll go into what a complex ion is in just a minute. So when a base like ammonia is added to this, it will react with the silver cation, therefore reducing the concentration of that ion in the solution. And what does that mean? Which way will equilibrium shift now that that silver ion's been kind of consumed a bit? Yeah.
Should dissolve more.
More of the solid should be able to dissolve to replace that free silver ion, right? Because it's been used up. It's locked away in the form of a complex ion. Cool, so we understand that. So the product is removed. The reaction will increase in the forward direction again. Any questions about this?
What is a complex ion?
Great question. I'm glad you asked. I'm magically going to create a slide just now about complex ions. Okay, here we go. Complex ions. And I have a good link to a fantastic website about complex ions called ChemGuide. It looks like it was made in like 1994, but he updates it every year, and it has all the knowledge you need for high school level 3 chemistry. So a complex ion has a metal ion at its center with a number of other molecules or ions surrounding it. So it can have neutral molecules that are attracted to that metal ion, or it could have other negatively charged ions attracted to that metal ion. So we have a bunch of complex ions here. So overall, the whole species has a charge. And oh, what kind of shape is this, where we have 6 water molecules attracted to an iron in the center? Yeah, octahedral, eh? And so we got another octahedral. Well, all these examples here are octahedral. They're not always octahedral. So you can see the formula here for this. This is iron with 6 waters attracted to the metal center. And you can see that the lone pairs are what are attracted to the metal center, because obviously negative charge is attracted to the positive charge of the metal. And you might be wondering what kind of bond is actually happening there. Is this an ionic bond, covalent bond? What is it? It's a form of a covalent bond, you could argue. It's a covalent bond that we call either a coordinate bond or a dative bond, or dative. I'm not quite sure how to pronounce it. It's one of those two where they're attracted to the center and they form a form of covalent bonding. But this is unique covalent bonding because we know covalent bonding is the sharing of 2 electrons. But if you look at these pictures, both electrons are coming from the same species. So each water molecule is donating a whole lone pair to make that covalent bond, whereas typically in molecules, when we make covalent bonds, there's typically 1 electron shared from one atom and 1 from the other to make a covalent bond, right? That's typically how we form them, a sharing of 1 electron each that shares and donates. But in this one, both electrons are donated by the same species to form that covalent bond. Nice.
The question I had before was, you asked me yesterday in your email to ask if you had copied into the exam.
Thank you. Haven't. I'll do it.
That's all right.
Yep.
You got time.
Yeah, I'll do it today. But yeah, thanks for reminding me. After this, we'll do that. So if you're wondering like where the charges come from, because if you look at the top right-hand corner, like any good diagram at level 3, when we're drawing these structures with charges, remember we practiced drawing polyatomic ions last term with structure and bonding, and we'd have to write the charge outside the square brackets, all that good stuff. If we look at this one, it has a charge of 3 minus. We could probably figure that out. It's not just some magic number. What's the charge of aluminium?
3 plus.
3 plus. And how many fluorides have we got?
6.
6. And each one has a 1 minus charge. So 3 plus. And you add 6 minus 1 charges to it? 3 minus.
Negative.
Yeah.
Interesting.
Yeah. So you can figure it out typically. It makes sense, right? Structurally, it makes sense. Cool. So that's what a complex ion is. Now, these are the ones you don't need to memorize, but will be given to you in the resource sheet on the exam. This list of complex ions will be given to you. Okay, but these are the 9 you should expect to encounter, not all of them, but 1 or 2 of them maybe at most, on the exam. So we just looked at the case, I think, of silver with the ammonia ligands attached to it. We talked about how the solubility of silver chloride would increase when we introduced ammonia, which is a base, but also able to form complex ions. Yeah.
What are ligands again?
So ligands are these species that bond around a transition metal in a complex ion that donate a pair of electrons. What?
Will we ever have to explain what ligands are?
No. Yeah, the ligands are the molecules or ions that bond around the central atom in a complex ion. Okay.
Does anyone else get like a random feeling of relief every time you ask a question? Do we need to know this? And you go, no.
So let's move on. Keep moving through it. So we answered this question, right? With silver chloride, we could increase the solubility when adding ammonia. Why? Because ammonia is what we call a ligand. It bonds around that central metal to form a complex ion, removing the silver from the system. So equilibrium shifts to the right, forming more products. More will dissolve. Cool. And we got, sorry?
NH3 and OH minus are the 2 ligands
Yes.
that are relevant to this exam?
There's one other some cyanide right there, CN, right?
Okay.
You see CN, that's typically it. But you can see a lot of these species have either ammonia or hydroxide. Just looking through it, we got lead, nickel, silver, zinc, aluminium, zinc again, copper, yeah. So there's just one instance where it's not hydroxide or ammonia. No, sorry, there's two instances of CN.
Okay.
Yeah. Cool. Complex ions. Done. Last one. This one's kind of the interesting one. Yeah.
Shouldn't it be Ag2CO3? The first one, shouldn't it be 2 Ag plus?
Thank you. Yep, you're absolutely right. That should be a 2 there. I'll
Ag+.
balance that afterwards.
Cool, thanks.
Yeah.
Isn't a mistake.
Yeah, please call me out when you see that. With the last one, it's kind of tricky. This did appear, I believe, on the regular level 3 exam recently, a couple years ago. It was a favorite problem I like to do with classes over the last couple of years because it did appear on an exam. I don't think it was a scholarship one. I think it was a regular level 3 exam when this question appeared, I believe. This question here where it asks you the exact same 3, like is it more or less soluble at each of these pH ranges?
It wasn't there on the last year's exam.
No, it was at least a couple of years ago, and I believe it wasn't scholarship, even though this seems kind of almost like scholarship level in terms of understanding. Okay, so we said at low pH we know what's going to happen, yeah? We know that, it's going to be really acidic, it's going to consume the hydroxides, so more will dissolve.
Yes.
pH in the middle, what's happening there? Okay, we'll figure it out. So, how do I update this? Yeah, okay, so if a salt like zinc hydroxide, which has hydroxide in it, if we have it in the pH range below 4 or 10, equilibrium shifts to the left to decrease solubility, and that's because in that range we have like a medium amount of hydroxide, not too much acid to neutralize the hydroxide. And the addition of these hydroxide ions as we slowly increase the pH from 4 to 10 means equilibrium shifts to the left because we're adding more product. We're increasing the product concentration of hydroxide ions.
So you increase solubility?
No, you decrease solubility. You form more precipitate.
Oh, okay. Wrong way around.
In the range between 4 and 10, you form more precipitate because you're increasing the concentration of free-flowing hydroxide ions, which is one of the products if zinc hydroxide is the precipitate we're looking at. Now, increased solubility happens, and this seems kind of contradictory at first, at a pH greater than 10. So if we keep increasing the hydroxide concentration, this weird thing happens where all of a sudden the solid's like, hey, I want to dissolve now. This is cool. There's lots of hydroxides in there, which is why I precipitated in the first place. But now, oh man, all these hydroxides, let's dissolve.
Sorry,
You'd be
I was saying my
perfect.
throat's hitting up. I was minding it.
And that's because
That's
that's because if you maybe just read the slide right there, or if you looked carefully at here, zinc hydroxide, if we react with enough free-flowing hydroxide ions in solution, we form actually a complex ion that's soluble because it's an ion, it dissolves. So if we overload the system, really high pH, lots of hydroxide ions are present, it forms a complex ion, and more will dissolve as a result of that. So because zinc ions are being removed, as we add hydroxide to form the complex ion, solubility will increase in the forward direction to replace that product. Cool.
So if you add too much, it makes the ion and pigment. Okay. That makes sense. What's between 4 and 10?
Forms more precipitate. Yeah. Equilibrium shifts to the left in that range because hydroxide is pushing it towards that. Okay, so we're going to stop right there for now and actually apply this to some problems. Ion effect is our next topic. In an aqueous solution, if that aqueous solution already contains either one of the ions present in a precipitate, maybe you're adding to it or that you're wanting to form, then that ion that's already present will reduce the solubility. Because, just like what we've been talking about with Le Chatelier's principle for the last hour, that presence of that ion shifts equilibrium to favor the formation of the reactant, quote unquote, the salt. It's not really a chemical reaction, it's a physical change when it dissolves, right? But it's formation, the left-hand side of this equilibrium, the formation of more salt. Because, with those ions there, we're increasing the concentration of one of the quote unquote products, so it favors the formation of that solid. So silver chloride would be less soluble in seawater rather than drinking water, because seawater obviously contains a lot of salt. And in salt, you have chloride ions, right? So in seawater, there's a large concentration of chloride ions. Those chloride ions will shift equilibrium to form more silver chloride. Less silver chloride would be able to dissolve than in drinking water or fresh water. Make sense? Some nods? Cool. And that's the basic principle of common ion effect. There is a common ion. That comes from the fact that, an ion in common with the formula of the precipitate and one of the ions it forms when it sparingly dissolves. And that same ion is present already in solution. So another common ion would be, can anyone give an example of another ion that might already be in water? Like that could be added if we add salt to water or if we use salt water. Chloride's going to be there. But what's another maybe anion that might already be present in some waters? Yeah.
Sodium and magnesium are pretty common.
Sodium, magnesium, okay, that could be a common ion. Chances are, though, sodium doesn't form any sparingly soluble solids with a lot of things. So you're thinking of which ions do we typically see in sparingly soluble solids? Magnesium sometimes, but what anions maybe come to mind that seem to be in water sometimes?
When you say anion, do you mean negative?
Exactly
Because
what I was
carbonate.
thinking. Fluoride.
Carbonate could be one.
Carbonate.
Fluoride doesn't form too many sparingly soluble solids. I'm thinking of,
Calcium.
calcium can sometimes form some sparingly soluble solids.
Calcium's not an anion.
We should look at our solubility rules, I think, a little bit later. I'm thinking like hydroxide. At certain pHs, you're just going to have a natural source of hydroxide.
Hydroxide already, sorry.
No, I've just said chloride, right, in seawater. But if you had fresh water, maybe the pH is a bit high in that water, and so the presence of some natural hydroxide ions would cause the shift towards the left, because if you have a common ion where some metal could precipitate out with that hydroxide. So let's apply this now to math, okay? We're going to do a little bit of calculations proving that when these common ions are present, solubility is reduced. So guess what we're going to be calculating? We're going to be calculating solubility when a common ion is present. So it's very similar to what we did last class, but we need to make sure our calculations include the concentration of that common ion. So here's an example. What is the solubility of silver chloride in this solution with a given concentration, okay? In a solution of salt water. Okay, so we know the concentration of the salt water, and we're just trying to figure out what S is equal to. So we're solving for S, same as normal, and we're given the Ks constant, the solubility product constant, that's given. And okay, silver chloride, what sort of ratio are we looking at for our equilibrium expression?
1 to 1.
It's just a 1-to-1 case, right? Now, in a 1-to-1 case, this is our expression where the concentration of silver is multiplied by the concentration of chloride, and it's all equal to that Ks constant, right? So, do we know either of these concentrations yet?
Yes.
Turns out we kind of do. We can introduce variables to represent the concentrations we want to solve for. So S for solubility of the overall compound, and because it's a 1-to-1 ratio, silver's concentration will just be equal to S. But chloride's concentration is different in this scenario. This is a one twist. It's very small. It's not a very difficult thing to do. You just need to add to the chloride ion the amount that dissolves from the silver chloride plus the amount that was contributed from the fact that it's in fresh water, or sorry, salt water, right? And so that concentration of salt is found here. So we know the concentration of chloride. We plug that number in there, plus the little bit that dissolves from the silver chloride. So now our equation looks different. But we're going to simplify it a bit because we're lazy chemists. If we were to multiply these two concentrations together, we'd get a quadratic.
Yes.
Because we would have S times, in brackets, this number plus S. So we would get S squared at some point in our equation. Chemists are lazy. Quadratics are hard to solve. Not really. You guys can solve quadratics. That's like high school maths. Chemists are really lazy, I guess. I'm making a joke about it because we can make a simplification that is valid, and we'll prove it's valid later, why this cheat code is fine to use. So here's the assumption we're going to make. We're going to make a few assumptions in this unit throughout the next few weeks. Our first assumption is assume all chloride ions, or whatever the common ion is, comes only from the one source that supplied that common ion, in this case the salt water, because there's lots of obviously chloride ions in salt water, and only a little bit that's actually going to dissolve from our silver chloride precipitate, right? It's sparingly soluble. Very little will actually dissolve. Most of that concentration of chloride comes from the fact that it's salt water and it's already there. Cool? So
you do have the concentration.
So this concentration of chloride here, that my mouse is around, let's just ignore S. Pretend there's zero contribution of chloride from our silver chloride, okay? So now our equilibrium expression reduces to this equation. It's the concentration of silver, that's where the S comes from. That's the concentration of silver, multiplied by the concentration of chloride just from salt water, pretending none at all comes from the silver chloride. Cool? And that's the assumption we're going to make, so we don't get a quadratic anymore. And this is easy to rearrange. We did the rearrangement down here. Plug it into your calculator, you should get the number in the box. It's concentration, so it's in moles per liter. So I'm saying that is the solubility of silver chloride with a common ion present. Cool?
Yes.
Cool. One thing I want to go over before we finish up this topic for today. Let's prove that this assumption is valid. Cool? So I made an assumption that all chloride ions only come from the source of the salt water. Let's verify if that's true. To do that, let's figure out how much would actually be contributed from the silver chloride in fresh water. So no common ion present, okay? So we know the Ks constant, same value we used last time, and it's equal to S squared in a 1-to-1 ratio. So when we rearrange it and take the square root of the Ks value to find S, we find the concentration is 1.26 times 10 to the negative 5 moles per liter. Very small, very small. It's like 100th of a millimole per liter. So what that means is such a small amount is contributed, it doesn't even change the concentration of chloride overall. Because we know the total chloride concentration is the amount from salt water, 0.0025, plus that very small amount that we just calculated. And you can see I've added 0.0025 plus that small amount we just calculated. And in the end, it rounds to the same number, 0.0025. Same number. The solubility, the amount that dissolved, was so small it does not affect our original number because it's to the power of negative 5, right? It's a very small number. So this assumption is valid. It has not changed our total chloride concentration.
And you can always use this assumption in the exam as well.
You can always use this assumption, yeah.
Are they wanting us to prove the assumption?
No, very good question. They'll never ask you to prove it or just to do a question to find out if it's valid or not at this level. At university, you would, given you don't know if you can make the assumption or not. Because with sparingly soluble solids, some are obviously very sparingly soluble and some are actually kind of soluble. You know?
The point is they
Yeah.
don't.
Yeah.
They're so not soluble that you can almost always assume in this unit that the amount dissolved isn't enough to make a difference.
So that's it. With this twist here, that's all we got to do. These problems are very similar to what we did last class. Just plug in the concentration of the common ion, pretend none comes from this precipitate that dissolves a very tiny bit, and we've proved that it dissolves in such tiny quantities that it doesn't affect the overall concentration of that common ion. And that's it. We'll do some problems next class. We'll continue this topic a little bit more and do some